Okay, so welcome back. I hope the quiz went well. Couple of quick reminders. So we actually have our next quiz a week from today. So quiz 2 is on February 17th. And I'll send a reminder about this after class as well. But quiz 2 is going to cover lecture sets 4, 5, and 6. Okay, so that's one-way ANOVA, comparison and contrast, and the CRBD stuff that we talked about in lecture set number 6. Actually, I'll think about that a bit. It's definitely going to cover lecture sets 4 and 5 because you had an assignment on those as well. So there's time to review. And I might add in the lecture set 6 stuff. I'll think about it for a little bit there. Okay, so we have our quiz next our second quiz, same format next Thursday. I'll send an announcement after class just to remind everyone, and I'll give details about the material it's going to cover. There's practice problem set already posted for it with solutions. So that'll take place during class, same format as the last quiz that we just had on Tuesday. We also have an assignment due tomorrow. So the third assignment is due tomorrow, and the second mini project is due tomorrow if you're taking part in that. And then there's a fairly big gap. So assignment number 4 is not due until March 4th. So that's after the reading week. And the second or the third mini project isn't due until March 11th, which is a week after assignment 4, which is also after the reading week. Okay, so quick turnaround quiz wise. So I think quiz 2 is going to be our last class before the reading break, if I have my dates correct. Just confirm that. Yeah, that's true. So we'll have quiz 2 next Thursday, and then we'll go into the reading break. And then we'll come back after that and continue on. All right. So quiz 2 next Thursday, assignment 3 tomorrow, and mini project number 2 tomorrow. And then assignment 4 and mini project 3 are not due until after the break. So we're moving along. We are still working through the ANOVA section of the class. So just slightly behind the course outline, but that's not too bad considering what's coming after we finish lecture set number 7. The non-parametric material is pretty quick, so we should be able to get back on time, finish on time without any issue. All right, and with that being said, I will get back into lecture set number 6. So we did a little bit of work from lecture set number 6 on Tuesday, just before we started the quiz. So this lecture set is about conducting completely randomized block designs. So just again, as a quick reminder, a completely randomized block design has the same goal as a one-way ANOVA. The only difference is that there's a confounding variable that's present in the experimental design, and we want to account for that confounding variable. So we create these blocks. In terms of the example we're looking at, the blocks are literally like rows in a field. And the purpose of the block is to extract the information from the confounding variable so that it isn't influencing the treatment that we are trying to study. Okay, so we actually looked at a comparison. So this is our CRBD ANOVA table on slide 15. And this CRBD ANOVA table can be used to test for a treatment effect in the same way that we did with one-way ANOVA. And we actually showed how that CRBD ANOVA table would compare to the one-way ANOVA table. So we have the comparison shown on slide 17 of our one-way ANOVA table which we can compare to the CRBD table. And we can see that the treatment and the total sources are exactly the same for one-way ANOVA. And the only difference is this block source is pulling information out of the error. Right. Okay, so we ran this one-way ANOVA test. We actually found for this particular experiment, it didn't, in terms of finding a significant result, or the conclusion, I should say, for this particular example, the conclusion didn't change regardless of whether we blocked or not, but you can still see the effect of the block variable. So you can see how the F statistic has gotten smaller and the p-value has gotten larger, which is reflecting the fact that you have pulled this information out of the error and put it into that block source. Now, one of the questions that would follow from when you run a CRBD, outside of the general question about significance of the outside of the question, is there a difference between the means of the treatment groups, was blocking effective? So last class, we started to work on this type of test. To answer this question, we can actually just run we can just run the F test about the block source. So that's what I have here on slide 18. We're pretty much done with this. We just need to write out the conclusion, but probably a good thing just so we can go over it again. But you can see here, basically, to answer that question, like, is blocking effective? All we have to do is test for a difference among the block means. So we have our standard hypothesis here, beta 1 equals beta 2 equals beta 3 equals beta 4, because we have 4 blocks and we're letting beta represent the mean or the effect from each of the blocks on the overall mean. And we can test that against the standard alternative. Not all the block means are different. And this is the same thing as asking, is blocking effective or not? So we're saying in the null hypothesis, if all the means are equal, that means that blocking was not effective. And if there is evidence of a difference, that would imply that blocking was effective. So we have our null and alternative, our significance level. Our test statistic is just the ratio of the mean squared block to the mean squared error. Both of these values I'm just pulling out of that ANOVA table at the start of the example. All right, here's my critical value result for this test. Okay, so this is the critical value. Okay, now we can also construct a p-value for the same problem. So in this case, we would take our test statistic. So we have F is 9.12083. So our p-value is going to be the area to the right of this quantity here. And so the p-value is the probability that F exceeds 9.12083. Okay, so if we go to our F table now, so we have 3 and 15 degrees of freedom. So here is 3. We can scroll down a little bit. Here's 15. So if we're looking for a p-value, we're working in this range of numbers here. Okay, so our F statistic was 9.12. So you can see that our value here is greater than the largest value that's listed in this column. So our F statistic is bigger than 6.48, which means that the p-value, or the area in the upper tail of interest, is going to be less than 0.005. So we can say, since the probability F exceeds 9.12083 is less than 0.005. The p-value is less than 0.005. All right. So based off of either approach, the p-value or the critical value approach, we can see that there is rejection of the null hypothesis. So then we can say something to the effect of, at the 5% significance level, the data provide sufficient evidence to suggest that blocking was useful. All right. Any questions? Okay, so that so now we have seen the two main tests that fall out of a completely randomized block design ANOVA table. So when we run a completely randomized block design, the goal of the procedure is really not all that different from the goal of the procedure actually is the same as the one-way ANOVA. Again, it's just the incorporation of that blocking effect to try and account for the confounding variable. So technically, in terms of experimental design, the design is slightly different from that of a one-way ANOVA because there is the presence of this confounding variable. So with one-way ANOVA, we had treatment and response. With block designs, we have treatment, confounding variable, response. Now, again, the goal is the same. So if we do reject the null hypothesis that there's no treatment effect, which effectively means that we have found evidence that there is a difference among the treatment means, we'll be interested in determining where that difference lies. So just like we talked about with the one-way ANOVA procedure, after we run the one-way ANOVA and we construct the F-test for the one-way ANOVA, we would then run a multiple comparison about the treatment means to determine where the differences exist if we found evidence of a difference. So with the block design, we can do the exact same thing. The only real difference here is that our contrast is going to be about the treatment mean exclusively. Even if we find evidence of a difference among the blocks, we're not going to be overly interested in exploring that because we're not concerned. We know that the block plays a role in how the response variable reacts to the treatment, but we don't need to study it carefully the same way we would with the treatment means, because the treatment means are what we're actually interested in. So if we find evidence to reject the null that there is a treatment effect, then we can run a multiple comparison about the treatment means. The multiple comparison about the treatment means start from the definition of the contrast, the same way they did after the one-way ANOVA. So here we have an example of a population contrast about the treatment means. So this is just the general expression. You'll see that this is the same definition we had when we introduced the contrast in lecture sets number 5. So we have gamma is equal to C1 alpha 1 ... plus CK alpha K. And then we have as long as the sum from J equals 1 to K of CJ equals 0. So this is the same definition we had before. Linear treatment means, and we're adding and subtracting them. And our only constraint is that the coefficients have to sum to 0. So this is not any different from what we studied with the contrast for the one-way ANOVA. And we can estimate this contrast using little c the same way we did before. And then here we're going to have the treatment means. Okay, so these are the sample mean for each treatment. Okay, so just a little bit of background. Basically, the margin of error for a contrast or a multiple comparison that's falling out of a CRBD is exactly the same definition as the margin of error for the one-way ANOVA. The one thing that's really nice about a CRBD is that the sample size for each treatment is actually just the number of blocks. So whenever we're running a multiple comparison following a completely randomized block design, you only have to do the margin of error calculation one time, because every single treatment is going to have the same number of observations associated with it, which is simply the number of blocks that are present in the experiment. So we talked about how completely randomized block designs are essentially square or rectangular designs, where you have the number of blocks, say, on the row and the number of treatments on the columns. That means every treatment has the same number of observations, which again is equal to the number of blocks. So when we're computing the standard error for our multiple comparison, and then computing the margin of error following that, we have the same formula that we had for the one-way ANOVA, except that the sample sizes are replaced with the number of blocks directly. And I'll show an example of this calculation momentarily. But again, the benefit of this is that you only have to make the calculation once, whereas with the one-way ANOVA, you have to change the margin of error depending on which treatments you're comparing, because each treatment could have a different sample size associated with it. Okay. So the process of setting up a contrast or a multiple comparison is going to be exactly the same with the CRBD as it was with the one-way ANOVA. In particular, we're going to be interested in running multiple comparisons about the treatment mean. This starts by choosing your experiment-wise error rate, and then determining how many comparisons you have, computing the individual error rate, so alpha star or alpha I, putting the means in ascending order, and then determining the margin of error for each comparison. Okay, and then you summarize the results in the usual way. So we can do this just by comparing the margin of error to the difference in the treatment means, for example. And then we can use things like those diagrams that show which means are the same, or we can just make up our own chart and say this is where the differences lie. There's lots of different ways that you can report the results. All right, let's look at an example. So we are going to compare the treatment means for the illustration that we've been working on throughout this lecture set. So we have 6 different treatments, and we found that there's evidence of a difference in the nitrate nitrogen content among those 6 different treatments. So the first thing we're going to do is declare our experiment-wise error, which is going to be just alpha from the CRBD. So that's 0.05. The second thing we're going to do is compute little m. All right, so little m is going to be equal to the number of treatment means, which we define to be little k, Okay, so this is going to be K choose 2, which is going to be 6 choose 2. Okay, so this is the same thing as 6C2. And that's going to be 15. So we are going to be making 15 multiple comparisons. All right. So the next thing we're going to do is figure out what is the individual error rate. So what is the error rate for each comparison? So this alpha star here is the same thing as alpha I. So this is going to be alpha E divided by 2m. So that's 0.05 over 2 times 15. So that's 0.00016. All right. Now, following the process strictly that we laid out on the previous slide, the next thing we would do is rank the treatment means. This step isn't entirely necessary. You can do the comparisons in order. So you can do 1 versus 2, 1 versus 3, 1 versus 4, 1 versus 5, 1 versus 6, 2 versus 3, etc. That's perfectly fine. We can also rank the means and then do the comparison in order of increasing means. It doesn't make a difference in terms of overall result. The only reason you would do it this way is because the differences would gradually get larger. So you would be able to kind of see like where the cutoffs are between significant and not significant differences. But you don't have to rank them is the point. That being said, I'll just follow the example. So we have our first mean, I can't rate threes anymore, is going to be 38.28, right? And this is for treatment 1. I'll mark the treatments after. Our second mean is going to be 39.51. Our third mean is going to be 40.62. Then we have 43.23. Then we have 44.03. And then we have 46.77. Just make sure I didn't make any mistakes there. Okay. And then just for reference, so this is treatment 1, treatment 5, treatment 4, treatment 6, treatment 2, treatment 3. Okay, so we're going to just do our comparisons in the order established here. So we're going to go T1 versus T5, T1 versus T4, T6, T1 versus T6, T1 versus T2, T1 versus T3, and then we'll go T5 versus T4, T5 versus T6, etc. So you'll be able to see kind of like cutoff points where things start to become significantly different, just because we are gradually looking at larger differences in the mean. This will make more sense momentarily, but that would be the only benefit of putting it in ascending order, is you can kind of see like where you can more naturally see where the cutoffs are. It might save you a bit of time in terms of calculation. Okay, so I mentioned before that the margin of error for a CRBD is a calculation we only have to do once. So the general formula here is going to be E is your T value on alpha I df error multiplied by the square root of the MSE multiplied by, or sorry, this would be EIJ multiplied by NI plus 1 over NJ. Okay, so that's the general formula. Because it's a CRBD, Ni equals Nj equals little b. So only in the situation that we're working with a block design would this work. But what happens is, because every treatment has the same number of observations associated with it, which is the number of blocks, all the sample sizes are just equal to the number of blocks. So this thing becomes T 0. Oh, sorry, I have too many zeros here. 0.0016, comma 15, which is the degrees of freedom, multiplied by the mean squared error, which is going to be 7.20. And then we're going to have 1/4 plus 1/4. Okay. Because in this particular experiment, there were 4 blocks. Right. Okay, so since T table doesn't give T subscript 0.0016, use T 0.005. So this thing is going to become T 0.005, comma 15, square root 7.2, square root 1/, well, and this is going to become 2/4, which is all right. So now we can go to our T table. Okay, so we're rounding to this quantity here, 15 degrees of freedom. That gives us 2.947. Okay, so this is going to be 2.947 multiplied by the square root of 3.6, which is going to be 5.591. Any questions? Okay. All right, so in table 6, we have the differences between the treatment means in terms of order. So just for clarity here, you can see we have treatment 1 versus treatment 5, right? So for T1 versus T5, we have absolute 38.28 minus 39.51. And this is the 1.2325. Right? So that's an example of the first quantity here. Right, and then this is the same pattern the whole way through, right? So for the second difference, you would have T1 versus T4. So this is absolute 38.28 minus 40.62. And this is 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. 2.3375. Okay. And then one more example. So let's just move it up a little bit. Let's say we do T4 versus T2. Okay, so T4 is 40.62 minus 44.03. And this is going to be the 3.4175, which is this value here. Okay. So these are examples of mean calculations. And now we're going to say checking for a difference. All right, so recall that no, it's all positive values. Yeah. So the two bars mean absolute, so that's strictly positive. Okay, so recall that the way the multiple comparison works is we have a confidence interval. Okay, so plus or minus E. So basically, if the absolute difference of x bar I minus x bar j is greater than E, then there is a difference. Okay, so what we can do, it's a little crowded, but basically the reason that we rank the means is because you can see now where the separation is. So our margin of error is 5.591. So we are looking for any value in our table that's bigger than 5.591. Okay, so here's 1. Here's 2. Here's 3. And here's 4. So you can see that basically the reason that we would rank the means is it just makes finding the values a little easier because they're all going to get stacked together based off of where, well, they're all going to get stacked together because we're working with ascending differences. But it would be just as easy if you didn't want to put them in ascending order, if you just use the natural order to just work through the table and look for those numbers as well. It doesn't change the result. Anyways, okay, so these are the 4 means that are different. So this part tends to confuse students a little bit, but I'll explain it nonetheless. Okay, so again, the bars here, when you have the means that are connected, so for example, we have 1, 5 is connected here. This represents no difference. Okay. So when you have 2 means that are connected by a bar, that bar connecting them is supposed to mean that they are the same. Okay. Okay. Now, with that being said, I admit that the line graph is somewhat of an unnecessary addition. From the table where we highlighted those 4 means, we've actually completed the problem at this point, because we now know treatment 1 is different from treatment 2, treatment 1 is different from treatment 3, treatment 5 is different from treatment 3, and treatment 4 is different from treatment 3. So the line graph is actually just an additional representation of the result, but it isn't necessary, in my opinion, given what we have in our table of means in shown above here. So from the table, we can actually conclude the test simply by saying, so we would have conclusion. Okay, so at the 5% significance level, the data provide sufficient evidence to suggest that the means of T1 and T2, T1 and T3, T5 and T3, and T4 and T3 are different. Okay. So I realize it's a little cramped, but what I wrote at the bottom here is, at the 5% significance level, the data provides sufficient evidence to suggest that the means of T1 and T2. So I'm just listing where we found a difference. So T1 is different from T2, T1 is different from T3, T5 is different from T3, and T4 is different from T3. Okay. And then T again represents treatment. So treatment 1, treatment 3, etc. Any questions? Okay, so if there's no questions, that brings us to the end of lecture set number 6, which was on the completely randomized block design. So the CRBD, again, has the same purpose as the ANOVA. So both the ANOVA and CRBD are meant to test for the effect of one treatment on a single response variable. The difference is that the CRBD includes information from what is called a confounding variable. So the block is meant to absorb the information from that confounding variable. The test that we are most interested in is the test about the treatment effect. If we reject the null hypothesis and state that all the treatment means are, that there's a difference among the treatment means, we can then run a multiple comparison about the treatment means to determine where the difference lies. And this is essentially run in the same way as with a one-way ANOVA, but the slight difference that we only have one margin of error calculation because every treatment has the same number of observations associated with it. All right. Okay, so as usual, there's an exercise at the end. So we'll start lecture set 7. So lecture set number 7 is our last lecture set in the experimental design portion. So there's 3 main topics in this section of the course, which are one-way ANOVA, completely randomized block design, and now two-way ANOVA, or the factorial design. What we're going to start off with is just a definition of what this is and how it differs from the previous 2 designs. And then what we will do is discuss what is called an interaction diagram. So the interaction diagram is a tool that we can use to assess the system that we are working with. It's valuable because it can give us an idea of where the differences potentially exist among the system. And it can also help us to understand which variables which of the explanatory variables are causing a change to the response as they interact with one another. After we go through this interaction diagram portion, we'll then look at the statistical model for the two-way ANOVA. And then we'll go through the usual sort of, or the familiar style of testing. So we'll talk about the associated hypotheses. We'll look at what's called a two-way ANOVA table. We'll discuss the different tests that fall out of the two-way ANOVA table. Then we'll discuss multiple comparison, and we'll talk about residual analysis. So most of the subsidiary, or actually most of the themes in this unit are exactly the same as the themes from the previous units. It's just a different type of design that's taking into account additional information compared to the one-way ANOVA and the completely randomized block design. Okay, so with one-way ANOVA, we have a single response variable and one explanatory variable. With the completely randomized block design, we have a single response variable, one explanatory variable, and one confounding variable. With the two-way ANOVA, or the factorial designs, we have a single response variable, but 2 explanatory variables. All right, so this is different from a CRBD because we now have 2 different variables that we want to account for. Factorial treatment designs are a general term to represent experiments where you have multiple explanatory factors. So the two-way ANOVA that we are going to study in this lecture set is, like the simplest type of factorial design because there's only 2 treatments. But you can have designs where you have 3 treatments or 4 treatments, etc. And those types of designs will gradually become more and more complicated because of all the different possible interactions that can take place in the design. So we're going to start with the simplest type of factorial design, which is the two-way design. So we're going to consider situations where we have 1 response variable and 2 explanatory factors. Okay, so the data set on slide 3 is a representation of this type of problem. So here we have the Iron Byron, which is a golf ball hitting machine. This was also a machine that was referenced in the practice problems for the first quiz. This machine is basically designed to smack golf balls so that they can test club and ball performance. The following data set is a result of using the Iron Byron to hit 4 different brands of golf balls. Obviously, the brand names have been taken off here. We're just calling them A, B, C, and D, but they could be things like, well, just name a golf ball brand, and you can imagine it might have been part of this experiment. And then they're also going to compare the distances between a driver and a 5-iron when smacking each of the balls. All right, so in this particular experiment, well, let's start by answering the question so that we can get an idea, and then I'll come back and sort of talk about some of the data here. But so we have 2 different treatments or 2 different explanatory values, which are the brand and the club. And then the distances that the ball traveled is the response variable. Okay, so just to summarize, I'll use the following questions here. Okay, so what are the factors? So the factors are the same thing as the explanatory variables. So just for clarity, okay, so our two factors are club type and golf ball brand. So the two variables that are coming together to create the response are the type of club that you're hitting the ball with and the type of ball that is being hit. And then from those two items, or from those two explanatory variables or two factors, we get the response, which is how far the ball traveled. Okay. Question 2. How many levels does each factor have? All right, so same definition of levels that we saw before. So club type has 2 levels, which are driver, comma, or driver and 5-iron, comma. Right. And then golf ball brand has 4 levels, which are A, B, C, and D. All right, how many treatment combinations are there? Treatment combinations refer to the total number of different influences on the response variable. Okay, so the treatment combinations, the formal definition is equal to equal number of levels of first factor times number of levels of second factor. So in this particular experiment, we have treatments combinations equal 2 times 4 equal 8. What is the response variable? So the response variable is the distance the ball traveled, which, or average distance the ball traveled, which would be in yards, because that's typically how, distance is measured in golf. Okay, so average yards. Ball. All right, so we have these definitions in place now. Let's just take a quick look at the data again so that we can make sense of these. So again, we have two explanatory variables, so two variables that we actually want to account for and study. This is different from a CRBD because in a CRBD, we would only want to account for one explanatory variable. The other variable would be considered a confounding variable. All right. Now, if we go back and look at the data here, you can actually see pretty clearly how things are laid out. So we have, we'll call this factor 2 is shown here. We have factor 1 here, right? And then the data inside the table that represents the response variables. Okay, so all right, so all these values in the table are responses. I mentioned before that we had those treatment combinations. The treatment combinations essentially represent the interacting levels of the two factors. Okay, so for example, okay, so we had 8 treatment combinations. So one of them would be the driver and golf ball brand A. The second one would be the driver and golf ball brand B. Then we would have driver, golf ball brand C. And inevitably we would end up with the 5-iron and golf ball brand D. All right, now the only other thing I want to mention here is you can see that for each of the treatment combinations, we have a stacked number of values, right? So for example, if we consider this set of values here, okay, okay, so these are 4 okay, so these are 4 replications at the driver A treatment combination. With two-way designs or factorial designs, replication is a natural part of the experimental design. Basically, for each of the different combinations, you have to have more than one value contributing to that measurement. So in this particular experiment, we replicated each of the different combinations 4 times. So for driver A, 4 balls were struck. For driver B, 4 balls were struck. For driver C, 4 balls were struck, etc. So this creates different sample sizes within the experiment. For example, there's 32 total observations, right? And then for each of the different clubs, there would be 16 observations, for example. So we have little nd is 16, little n 5-iron equals 16. And then you can continue to break this down in different ways. For example, little na, which would be the sample size for golf ball brand A, that's going to be 8. And that would be the same for B, C, and D. So we have a sample size for each main factor. So the brand and the club type. We have an overall sample size, which is just the total number of observations in the experiment. And then we also have sample sizes which represent replication at each treatment combination. So there's quite a bit of information within these designs, and there's a lot of definitions is the other thing. Any questions? All right. Okay, so what we're going to do next is look at two different illustrations to highlight three different definitions. So the purpose of this next discussion is to set up interpretation of what is called the interaction diagram. So an interaction diagram is a common tool that is utilized in experiments where we have multiple explanatory factors. And the purpose of the diagram is to give us an indication of how the response variable is reacting to the factors that we are considering. So to understand how an interaction diagram works, there are three definitions that we, there are three terms, I should say, that we will define. They are the simple effect, the main effect, and the interaction effect. All three of these terms can be defined through what is called a table of means. So an example of a very simple table of means is given at the end of slide 5. So we have here a 2x2 table. So this is a situation where we have two factors, factor A and factor B. Each factor had two levels associated with it, low, high, and that creates 4 treatment combinations, right? So same definition that we had just established for the original example. But in this situation, it's a much simpler scale. So we have 4 total treatment combinations, and the values inside this table are representing the means at each of those treatment combinations. So there would have been some number of replications at each combination, and we've just taken the mean of those replications. So the first term, which was simple effect. The simple effect is just the difference in means between two levels fixed at one level for the other variable. So for example, we have, and I'll just pull, I'm just gonna sketch out the contingency table here for reference. So we have A, low, high, B, low, high. So we have 20, 40, 30, and 50. All right, so for example, the simple effect of factor A for low factor B is 40 minus 20. So basically what we're saying here is we're holding fixed at low factor B. Okay, so I'll mark this one in green. Okay. So that's this part here. So we're just holding fixed at one part of B and then looking at the difference between the levels of A. Similar definition here. So the simple effect of factor A for high factor B is 50 minus 30, which is 20. That's just this part here. Okay, now we're going simple effect of factor B for low A. Okay, so now we're going across here and we're looking at this difference. So this value here would be 30 minus 20 equals 10. Okay, and then we have simple effect of B for high A. So now we're going across this way. So we have 50 minus 40 equals 10. Right? So the simple effects, very briefly, are just the differences between two levels of one factor while you're fixed at the other factor. And this, hopefully this color-coded example makes sense. Okay, so the main effect is actually something that we're going to be more interested in. The simple effect definition was just to help us establish sort of a baseline for determining how we're going to compute these types of differences. The main effect is actually a value that we're going to be able to see directly, or we're going to be interested in studying, because main effect differences represent differences in treatment means. So the main effect is the average difference across two levels of one factor compared to the levels of the other factor. So for example, in our little 2x2 contingency table, the main effect for factor A is the average at its high value minus the average at its low value. So you can see here we have 40 plus 50. Those are the two quantities that make up high factor A, minus 20 plus 30 over 2, which are the two quantities that make up the low factor A. So 40 plus 50 over 2, minus 20 plus 30 over 2, and that gives us 20. So that's the average difference between high A and low A. All right. So the main effect for factor B is going to be the average at high B. So this is going to be 50 plus 30. Minus the average at low B, which is going to be 20 plus 40. All right, so we have 50 plus 30, which is 80 over 2, which is 40, minus 20 plus 40, which is 60 over 2, which is 30. So that gives us 10. So main effects are average at the levels of one factor compared to one another. Right. Any questions? So in all of the illustrations that we did on the previous slide, I purposely always went high minus low for the different simple effects and the main effects. We can see that as we transition from low to high in this particular system, everything is positive. So it's basically showing us that the movement from low to high is always in a positive direction. For the main effect, it's the same thing. So for the main effect for factor A, we found that as we transition from low A to high A, the value got larger. For B, it's going to be the same thing. So we found here, so we can show the calculation. When we took high minus low for factor B, we have a positive number. So the main effect for factor B indicates the average response increases as we shift from low B to high B. Okay, so in this particular system, what we have observed is that as we move from low to high, all of the simple effects go in the positive direction and all of the main effects go in the positive direction as well. So this would be a system where you have no interaction. And this can be represented through the interaction diagram, which is shown on slide 8. Okay, so in this diagram, we have factor A on the x-axis, and then we have 2 points, low, high. And then we have factor B being indicated by the type of line. So the dashed line represents a high factor B, and the solid line represents a low B. And then on the y-axis, we have the average response values. Okay, so for example, this point here is going to be 50. Here, again, I'll just sketch the contingency table for reference. All right, so we have 20, 40, 30, 50. Okay, so you can see this top point here is 50. That's the high B. This point here is 40, which represents high B, or sorry, this would be high A, low B, right? And then the 50 here, sorry, is high A, high B. This value here, which is 30, this is going to be the high B, low A. And this value here, which is 20, is low B, low A. Okay. Just for reference. Okay, so we talked about the idea of those main effects. The main effects are actually just the averages of the two lines and of the stacked points. Okay, so if we were to draw 2 dashes here, so these should be perpendicular. This is main effect, or sorry, this is average of low B this is average of high B. And then if we do 2 stacked lines here, this is average of high A, and this is average of low A. Okay, so the purpose here is that now you can see visually what we had already determined mathematically. As we move across the lines, so for example, as we move from low A to high A on the high B line, we get bigger. As we move from low A to high A on the low B line, we get bigger. As we move from low B to high B at high factor A, we get bigger. As we move from low B to high B at a low factor A, we get bigger. And the averages for those effects, so the average of low B is less than the average of high B, and the average of low A is less than the average of high A. So everything is moving in the same direction. So this is a system where we would not have interaction, and this is what we would call a system of parallel lines. But all of the terms that we defined before are being represented in this interaction diagram. So the simple effects are when you move across the lines or you move between the stacked points. And the main effects are looking at the averages of the lines or the averages of the stacked points. And everything is going in the same direction. That's the key. This represents no interaction in the experiment, or there's no interaction between the factors as they influence the response variable. Right. And again, the other thing is construction of the diagram is literally just plotting the means from that contingency table. Okay, so on slide number 9, I'm just highlighting the points I had just made. So this is just a summary of what I had just verbally explained to you. So why you can see where the main effects are and why you can tell there's no interaction. Basically, if you have parallel lines, that represents lack of interaction. And the main effects are differences between the stacked points or the averages of the line. But I'm going to come back and show more examples of how we can diagnose this a little bit later. Okay, so to illustrate what an interaction effect looks like, we're going to look at a different example. So the first example that we considered, there was no interaction in that experiment. And we determined that through the fact that our interaction diagram shows parallel lines. To understand what interaction looks like, we're going to use an experiment where we are measuring the tensile strength of asphalt, and we are comparing the asphalt across 2 different factors, each with 2 levels. So we are considering what material was used to mix the asphalt together and how the asphalt was actually compacted. So we have compaction method versus type of specimen or type of mixture. And then we are measuring the strength of the asphalt. Okay, first off, if we were to go through and compute the main effects and the simple effects for this particular experiment, what we would observe is that there's a contradiction. So for example, the simple effect of the aggregate type on tensile strength with static compaction is -3. The simple effect of aggregate type on tensile strength with kneading compaction is +37, and the main effect is +17. So we have a contradiction, or we have a difference in direction between a main effect and the associated simple effects. This is the first hint that interaction might be present in this experiment. Okay. Now, what we could also do, and this would be the more direct way, is build the interaction diagram for this experiment. So if we do that, we end up with the following. Okay. So I will, just for reference, I'm going to pull that table over again so you can see the values. Okay, so we have A, and then we have A1, A2, B, B1, B2, and then we have 68, 65, 60, 97. All right. So this is our value 97 here. So again, this interaction diagram is really just a representation of the means. This is going to be the 68. Or sorry, this is the 65. Here is 60, and here is 68. Right, so these diagrams, again, they're just plotting the means for the experiment. Okay. And the key takeaway here is what you can see is that this diagram is showing us that the lines are not parallel. And the lack of parallel lines represent that there's an interaction present within the experiment. Right? So this particular plot is showing us that there's evidence of an interaction. Now, the other thing we can do is, again, we can highlight the average changes. So these two dash points and these two dash points represent the averages across each of the different levels of the treatments, of the treatment categories, or the treatment levels. This value here, this dash line here, I'll just label, so this will be 1, 2, 3, 4. Okay, so 1 does not equal 2. So that is main effect present. And then similarly here, you can see 3 does not equal 4. So this is main effect present. Okay, and then we have crossing lines, which indicates interaction. So diagnosing interaction diagrams is not, it's not trivial, but it's not super complicated, let's say, for lack of a better term. Basically, what you're doing with these diagrams is, one, you're looking for line segments that are crossing or parallel, and two, you're comparing averages of the stacked points and averages of the line segments. If the averages of the stacked points or the averages of the line segments are the same, that represents no main effect, which would be the same thing as, like, in an ANOVA experiment, that would represent no difference among the means. And then if those values are different, that would represent a main effect, which would be basically a difference in the means. So we're going to tie the diagram into the ANOVA analysis in what is to come. But the first thing is just to understand how to interpret the diagrams. When we meet again on Tuesday, because I'm not going to have enough time to finish this today, we're going to go through an illustration where we work through diagnosing all of these diagrams based off the definitions that we just learned. All right, but I will stop here today. Just note that slide 13 is just summarizing again what I just expressed verbally. So I'll mark our stopping point as here. Okay, and then on Tuesday, we'll come back and review this briefly, and then we'll go through an example where we diagnose each of those interaction diagrams, and then we'll start with the study of the actual two-way ANOVA experiment, so the hypotheses and the table, and then we'll tie together the interaction diagram and that procedure. All right, so assignment 3 is due tomorrow. Mini project 2 is due tomorrow. We're going to have quiz number 2 next Thursday. I'll send out a reminder about that. And we'll just make it lecture sets 4 and 5 since we haven't had an assignment on the CRBD stuff yet. So I'll send out an announcement about that too. There's practice problems posted. The last problem in the practice problems is the CRBD. So you don't need to do that one for this quiz, but I'll send out, or actually I'll just repost them. That'll be easier. And then that's it. That's all I can think of for now. So I have office hours tomorrow. And if I don't hear from you before, I will talk to you on Tuesday, and have a good weekend and enjoy the Super Bowl.